Fragments. That's all we have now. Scraps and pieces, scattered through the historical record like so many leaves on an early fall day. They tell us of a great intellectual endeavor undertaken by many to understand the world in a rational and predictable way. Between the massive compendium of the writings of Aristotle and the hugely influential work of Claudius Ptolemaeus half a millennium later, there were brilliant minds who worked in the areas of mathematics, physics, astronomy, and geography, and who wrote of their investigations so that their fellow lovers of wisdom could consider and critique their ideas. All we have left of most of these works are quotations in other, later writers. There was Aristarchus, who proposed a heliocentric model of the cosmos and an estimation of the sizes of the sun and moon. Archimedes developed a series of mathematical, physical, and engineering insights that may have prefigured the work of Isaac Newton by nearly 2,000 years. In the 280s BCE, an astronomer by the name of Timocharis made detailed observations of the positions of the stars that Hipparchus would use 100 years later to establish one of the most subtle motions of the heavens. Apollonius showed the equivalence of two geometrical models of the sun's motion based on earlier work, and both Eratosthenes and Posidonius made astronomically based measurements of the size of the earth. It would be a remarkable collection of intellectual achievement if only we still possessed it. But from these men, we have almost nothing of their original work. With the exception of Aristarchus' original calculations to determine the sizes and the distances of the sun and moon, and Hipparchus' commentary criticizing the phenomena of Eudoxus and Aratus, all of our references to their work are found embedded in the later writings of Greek and Roman authors, such as Plutarch, Pliny, and Ptolemy. In fact, in pure geometrical astronomy, we find a mini dark age between the work of Hipparchus, done at around 130 BCE, and the great synthesis of Ptolemy in 170 CE, a period of 3 centuries, a time longer than the United States has been a nation. And given the work we know that we've lost, how much is there that we don't even know about? Maybe the mini dark age wasn't dark at all. Maybe there are other gifted astronomers whose work didn't get recorded in other, more lasting documents. And if that's true, where did all of the work go? Did it exist, and if so, how and why was it lost? And what might remain? To answer these questions, we need to return to the world built by Alexander the Great, and the men who followed him to better understand what may have once existed and just how much has vanished. And also, we need to look and to learn what survived, because it forms the basis of the next millennium and a half of astronomical knowledge. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 8, The Great Syntaxis. One of the great traditions of college is the late night, deep philosophical discussion. It's where you and a group of friends get together to study, end up sitting around a half-furnished apartment, talking about the deep questions of life. One of the questions that gets asked pretty often is the whole, If you can invite 4 people to dinner, who would you invite kind of thing. Everyone goes around and gives their answer, and you always want to be the person that goes last, so you don't have to deal with the whole giving your 4 early and then having to change your mind when someone thinks of something else that you wish you had mentioned. You know what I mean? Another one of those types of questions is, if you could go to any one place and time in a teleporting time machine, when and where would it be? It's an old standby, a lot like that who you'd invite to dinner question. Except, if I can give you a piece of advice, never ask it in a group of history types, because they sometimes end up mad, or sad, or a little bit of both. It's really a mood killer. One of the Facebook groups I belong to is a group of history podcasters and podcast fans. The question got asked there once, and there was basically one common answer. As soon as it came out, it was surprising how many people confessed to getting mad when they thought about it. You may be thinking about it now. When and where would you go? And what if you could take a cell phone? I've known that answer, what I would say to that question, for a very long time. Sagan talks about it in Cosmos as the one place he would have wanted to go. Do you know what I'm thinking about? Actually, there are 2 places for me. Either one would be just as good, I think. I'd either like to go to the Library of Alexandria around the time of Ptolemy, say 150 to 200 CE, or the House of Wisdom in Baghdad, about 8 centuries later. If I got to carry my cell phone with me, I'd take pictures of as many scrolls as I could before my memory filled up or my battery ran out. What documents would I photograph? For me, I'd want to know about the works of all the people I mentioned in the introduction to the episode. Most especially, I'd want everything Hipparchus wrote. Then Aristarchus and Archimedes, and then I'd go looking for as many other writings as I could find of astronomers in that mini dark age, if they existed. There's so much I'd love to know, so much that's been lost to us, consigned to the speculations of history. The library was a product of an idea, a commitment, and, initially, a rivalry. When Alexander the Great began to conquer the world, he took the rationalizing impulse of the Greeks with him. Nowhere was that rationalizing impulse more embodied than in Athens, with the Academy and the Lyceum and the various schools of philosophical thought, such as the Stoics and the Cynics and the Epicureans. It offered an alternative to the superstition of the many mystery religions and religious cults and the superstitions and supernatural forces around the Mediterranean at the time. Combined with the record-keeping and administrative talents of Persia and Egypt, it held out the promise of a great empire of laws and trade, where an understanding of the world would lead to a better condition for all of Alexander's subjects, a sort of Persian, Egyptian, Greek Enlightenment. When Alexander's empire fragmented after his death, his greatest general, the one who claimed Egypt for himself and dared others to take it, Ptolemy I Soter, determined that he would create a kingdom that would eclipse the others in all ways. This included a city that would outshine both Athens and Babylon in its artistic and intellectual achievements. Thus, Ptolemy I, like so many others in history before and after this point who were involved in regime change, elected to select a new capital from which to rule rather than appropriate one of the older pharaonic cities such as Memphis or Thebes. The place he picked was the port Alexander had begun to build near the mouth of the Nile, one of the many cities he had named for himself, Alexandria. Here Ptolemy I gathered the finest and most talented artisans he could get, and supported the most innovative merchants he could entice, and he built a magnificent city of marble, laid out rationally, with a great lighthouse to guide ships into the great harbor. He also decreed that a temple to the Muses be constructed, and with it, a repository of all they represented, the accumulated knowledge of first Egypt, then the Mediterranean, and then the known world. Under the leadership of his son Ptolemy II Philadelphus, the temple and library would add a research institute and a second repository known as the Serapeum. It was decreed that all merchants would turn over any written works to be copied and then returned. This included maps, logs, and of course, all of their books. Some accounts have the institution as having over 1 million documents at least one point in its history. The Research Institute attracted the best and brightest scholars from around the Mediterranean, either to join the permanent staff or as visiting philosophers. Students came as well, to learn from the great minds gathered there and study the accumulated knowledge and wisdom the library housed. Of course, there were other large libraries around the Mediterranean, in Athens, on Rhodes, at Babylon, and in a couple of cities in Asia Minor. But if the ancient writers of the Roman Empire are to be believed, Alexandria was the greatest city in the remains of Alexander's empire, and the library there was the greatest institution of learning. When the Romans took control of the region, they sought to copy much of Alexandria's brilliance, but they never approached what the library represented. The Roman mind gravitated towards administration and law, engineering and timekeeping, rhetoric, and to a degree, logic. There was no place in the eternal city for a temple devoted to knowledge and learning, and so Alexandria remained unique in the empire of Mars. It's all gone now, of course. The world is a violent place, and the centers of learning often become collateral damage in the vicissitudes of warfare. Mars cared not for the daughters of Apollo, and so too the minds of his children. While one version of the story goes that the library was burned in the 4th century CE by a Christian mob led by a Coptic bishop, this is almost certainly an exaggeration. The truth is, the library was damaged or destroyed by conflicts on several occasions, including once by Julius Caesar during his stay there to help resolve a civil war. And while it was rebuilt or reconstituted each time, the truth is that eventually the entire civilization collapsed, and as it failed, the institutions it valued were left more and more vulnerable to neglect and plunder until, in the early 7th century, they were finally eliminated completely. Nevertheless, the loss is still strongly felt for those who value a historical record. That includes astronomers and historians of science, who wish they could reconstruct the trail of knowledge creation and model construction for the time between Aristotle and the astronomer Ptolemy, who, by the way, should not be confused with the Ptolemies of the Hellenistic royal line that ruled Egypt. And so it is that modern scholars work with scraps and fragments and wonder what might have been. Maybe, too, on those philosophical nights when the textbooks and study notes are piled up high around a rickety old table in a 2-bedroom college town apartment, students long, just a bit, for a teleporting time machine and a cell phone and this lamp. So, let's return to the historical narrative we have reconstructed from the fragments left to us. While we've discussed the work on solar and lunar theory done by Hipparchus, working from the mathematical models of Apollonius in the previous episode, there are many more contributions we know that the Rhodesian astronomer made. First, he compiled a very accurate star chart, a sort of map of the heavens, complete with a scale for brightness of the stars that we still use with some modification today in our system of astronomical apparent magnitude. The scale ranks the stars in order of brightness, with 1 being the brightest and 6 being the dimmest. He thought, too, because of the way the eye perceives point sources of light, that brightness was directly correlated to size. Magnitude 1 stars were bigger, he thought, than magnitude 6 stars, something intuitively logical if one thought that all of the stars resided on a sphere a long ways away from the Earth. Second, he developed instruments that would allow him to measure things like the points of the equinox, which will become important for what we'll discuss here in a moment. Third, he expanded on Babylonian eclipse tables and refined the estimations of the size and distances of the sun and moon from Aristarchus's measurements. Fourth, while his work developing solar and lunar theories is what is most important to our story, arguably his greatest contribution was actually in establishing what is known as the precession of the equinoxes. Precession is the observation that the point on the celestial sphere where the path of the sun crosses the celestial equator drifts from east to west around the equator over time. Now, that's pretty complicated, so let's unpack this idea, as it will be important to our story going forward for some time. As a quick reminder, recall that in our geocentric model of the cosmos, there is this great celestial sphere where all the stars reside that can be marked with a grid that corresponds to latitude and longitude coordinates on the Earth, including a north and a south pole and an equator. In a way, think of a huge basketball. Okay, so the sun then is said to travel on its own sphere that is tilted to the celestial sphere by about 23 degrees. Both of these spheres turn on their axes around the Earth from east to west. The celestial sphere turns once every 23 hours and 56 minutes, while the solar sphere turns once every 24 hours. The sun also moves on the equator of its sphere on a circular path that we call the ecliptic, about 1 degree per day. Moving on that path, the sun will cross the celestial equator twice a year, once going from south to north on the celestial equator in the spring, and once going from north to south across the equator in the fall. These crossing points are called the vernal and autumnal equinoxes respectively, and the days when the sun is at these points have equal lengths of daylight and nighttime. What Hipparchus discovered was that the points where those crossings happen drift very slowly around the equator. The rate is about 50 seconds of arc, or just a little less than 1/60th of a degree per year. Another way to say that is that the vernal equinox will move 1 degree along the celestial equator every 72 years. Right now, the point of the vernal equinox resides in the constellation of Aries. In Hipparchus' time, the equinox was actually in the constellation of Taurus. In all, the equinoxes will take about 26,000 years to travel all the way around the celestial equator once. This precession also means that the place on the celestial sphere where the Earth's North Pole points changes as well. While it points very close to Polaris now, in the time of the earliest recorded measurements of the Egyptian pharaohs, it pointed at a star we call Thuban in the constellation of Draco. The clue that Hipparchus finds that points him in the direction of this phenomena is a set of Babylonian observations of the star Spica in the constellation we call Virgo. These observations gave a position for Spica that was pretty different with respect to the vernal equinox point than he thought it should have been. He then reviewed the observations of an earlier astronomer by the name of Timocharis of Alexandria, who had recorded the position of the star in roughly 280 BCE. He trusted Timocharis' observations, and so he compared them with his own between the dates of about 147 and 127 BCE. In doing this, he realized the star seems to have drifted about 2 degrees with respect to the vernal equinox point in the intervening 130 or so years. This gave him a lot of confidence that the position of the equinox was changing over time. From this, he set out to construct an instrument that would allow him to very accurately determine the time of each equinox during the year. Over the next several years, he was able to establish the drift rate of the equinox points on the celestial equator with fairly high accuracy. As he put it, quote, not less than 1 degree in 100 years, unquote. It's a truly impressive piece of astronomical work, combining both observational and mathematical acumen. Unfortunately, the, quote, not less than, unquote, part of his prediction ends up being dropped, which leads to the use of an inaccurate drift rate or precession rate for many years until corrected much, much later. To these astronomical achievements, we can add work in geography and mathematics to the list. Without question, Hipparchus was one of the foremost intellectual figures of his time and arguably the greatest observational astronomer in antiquity. As a researcher, he combined the high level of accuracy of the Babylonian observational tradition with the Greek drive to produce workable geometric models of planetary motion to push astronomy forward by leaps and bounds. He seems to have understood that while the Babylonian astronomers had the best observations, they never attempted to create working models to assist them in their predictions of planetary motions. He also recognized that while the Greek mind had a knack for seeking patterns, the influence of Plato's theory of forms made for sloppy data-taking to inform the geometrical models those patterns produced. In a sense, he was able to synthesize the two approaches so that the strengths of each tradition covered the weaknesses in the other. And while there is some question as to how he was able to obtain the Babylonian data so much earlier than others, I would suspect that working on the island of Rhodes, which is just off the southern coast of Asia Minor, would have made acquiring that data much easier than if he had been in another part of the Mediterranean. One of the other things that Hipparchus' work illustrates is the growing influence of Babylonian astrology in the Hellenistic world. As the political situation in the eastern Mediterranean became somewhat destabilized after the collapse of Alexander's empire, there was a desire to know what an increasingly unpredictable world would hold. Driven by the very human need to feel in control of our circumstances, the idea that the unchanging heavens could hold within them portents and omens became very attractive. However, the predictions would only be as good as the models that enabled them, and by the time of Apollonius and Hipparchus, the old arithmetic and geometric projection models of the Babylonians were seen as being somewhat inadequate. While the accuracy of their predictions in the short and medium term wasn't bad, the models were ad hoc and a bit arbitrary seeming, something that would have been anathema to the Greek mathematician. Now, I don't know if this is what drove Hipparchus' quest for greater and greater accuracy, or if those were products of his own intellectual curiosity, but the desire for better models derived from the fruits of all parts of Hellenistic culture certainly influenced the resources and individuals going forward. Nowhere is this integration of astrology into astronomy more evident than in the work of Claudius Ptolemaeus of Alexandria. We don't know much about the life of Ptolemy other than he was born around 100 CE and he died some 90 years later. We have no record of him living anywhere other than Alexandria, where he may have been associated with the library for a time. What we do know is that he was a gifted synthesizer of previous knowledge and a scholar in his own right, who wrote three great works of lasting impact: Mathematicae Syntaxis, Geographica, and the Tetrabiblios. Along with these were a number of lesser works, including something known as the planetary hypothesis, that laid out his view of the cosmos. As a historical side note, it is between Hipparchus and Ptolemy that we have the gap that I mentioned early in the episode. For almost 300 years, there's no indication of new or innovative thinking in astronomical model building. While both Eratosthenes and Posidonius made their measurements to determine the size of the Earth, this seems to have been part of a broader geographical project rather than anything specifically astronomical. This is not to minimize or trivialize that work, as it is pretty groundbreaking, but it seems odd that we have no record of anyone taking up the biggest problem Hipparchus left unsolved: the orbits of the minor planets. As a way of illustrating this, in doing my research, I've come across a number of statements regarding Hipparchus' work to develop a planetary theory to go along with his solar and lunar theories. And I think the best quote comes from C.M. Litton's book, From Eudoxus to Einstein, A History of Mathematical Astronomy. He writes, quote, "Hipparchus did not achieve a satisfactory theory for the motion of the 5 planets. Partly this is due to the fact that he, unlike many of his predecessors, had examined sufficiently many observations over a period of many years to realize that the motions were exceedingly complex, with, for example, retrograde arcs, the lengths of which vary according to the position of the planet in its orbit." Unquote. In other words, while Hipparchus could do a very good job of modeling the sun's motion and the moon's motion, he wasn't able to get anything more than a generalization of the different epicycle model for the 5 minor planets. As we've mentioned in previous episodes, the key phenomenon one has to account for here with these minor planets is their retrograde motion. The different epicycle model is the most obvious way to do that in a geocentric model, and Hipparchus was able to show how one could produce retrograde motion mathematically. What he couldn't do was work out the specific model parameters for any of the planets that would have produced what is seen in the sky. These parameters would be things like how big is the deferent for the orbit, how big is the epicycle, how fast do each of the spheres turn, etc. This is pointed out not to lessen Hipparchus's work, he had plenty of other research to keep him busy, but rather to raise the mystery of why we don't have a record of anyone else picking up the problem for the next 300 years. Surely there were other gifted people working on astronomy during that time. One explanation that has been put forward is that maybe there were gifted individuals working on astronomy, but that when the Roman Empire swept around the Eastern Mediterranean, first through Greece and then Asia Minor and the Levant, they would have taken many of the best and brightest as slaves. Only in the most stable of regions, a place like Alexandria, or a political entity already aligned with Rome, would work have been able to continue. A variant of this idea is that even if they did produce work, when a town or city was conquered by an invading army, it was often plundered or razed, a process that involved a lot of destruction of the less permanent aspects of a civilization or settlement. Could it be that the work of some brilliant thinker went up in the fires of some conquest, while the man himself was placed in chains to become the tutor to the children of some patrician family in Italy? The other general hypothesis is that these works did exist, but they were subsumed into later compilations that synthesized a lot of different ideas into a coherent whole, and in doing so, disassociated the advancements from the people who developed them. The evidence that this is what may have happened can be found in a lot of Hipparchus's work. The notion is that it was incorporated into Ptolemy's Almagest so completely and comprehensively that for most scholars, the Almagest would suffice as a repository for the knowledge. And so the ideas, the complete ideas of the earlier mathematician were only kept in those repositories devoted to accumulating and storing knowledge. When those repositories were destroyed, so were the only existing copies of the original work, and all we are left with is what was included in that later piece of research. This might be especially true in cases where the synthesizer was associated with a specific intellectual tradition or institution, say the Library of Alexandria, and thus would have only sought to mention the contributions of the natural philosophers and mathematicians who had worked at that institution for a time. In the classical world, the idea of assigning credit was a pretty loosely run thing, and philosophers borrowed from each other liberally, occasionally only making passing reference to others who worked in their areas of inquiry, oftentimes just so that they could specifically contradict them. That names would have been lost might be surprising to us given our modern ethic of giving credit where credit is due in all cases, but in the ancient world it wasn't that uncommon. So, returning to the work of Ptolemy, let's take a look at the books he is best known for. The first of these is the one that everybody knows about, the Mathematicae Syntaxis, though it is usually known by that other name that we've mentioned, the Almagest. As a quick digression, let me answer a question I often hear from my students, which is how do you get from Mathematicae Syntaxis, or in English, mathematical treatise, to the Almagest? The work is, first, a comprehensive recounting and synthesis of the work done by previous astronomers, as we've mentioned. It then profoundly extends this work in a number of ways to provide a model for planetary motion for all 7 of the planets, including the 5 minor planets. Due to this level of insight, the work becomes known more simply as the Great Treatise, or E Megale Syntaxis in Greek. In time, the title evolves from great to greatest, or e majeste syntaxis. When translated into Arabic in the 7th century, the definite article al is added to a slightly altered version of this title, so you get Almageste. Finally, when this is translated back into Latin, it becomes Almagest. In a very cool way, the journey of the title of this particular piece of scholarly work contains within it a synopsis of the story of the history of scientific thought from the late classical period through to the Renaissance. So what made this work so special? As we've said, in it we find a complete summarization of Aristotle's original model and then the steps through to Hipparchus. From this point, Ptolemy develops an improved model, at least in certain respects, to predict the motion of the planets through the zodiacal constellations near the ecliptic. Now, there is some scholarly debate about how much of the work is original to Ptolemy. In this, there has been a, how shall we put it, vigorous discussion for nearly 200 years in the history of science. If I tried to cover the scholarly debate in full, I could do a full-length episode on that topic alone, so I won't try to go into all of the details here. For those who are interested in such things, I would recommend James Evans' discussion of the back and forth in his book, The History and Practice of Ancient Astronomy. But let me kind of give you the bare bones. On one side of the debate are those who claim that Ptolemy was a legitimate astronomer and mathematician who made his own observations and constructed his own models from superior data. On the other side are historians who say that he was little more than a plagiarizing hack who did nothing more than pull together the work of other natural philosophers and mathematicians, put it in a book in some kind of logical order, and then take credit for it all. The heart of the debate lies in the star chart that Ptolemy includes in the Almagest. Consisting of just over 1,000 stars, it gives the coordinates of each star as well as each star's apparent magnitude. The detractors say that all Ptolemy did was take Hipparchus' star chart, correct for precession, and then publish it. Others have pointed out that Ptolemy's star chart includes more stars than Hipparchus' would have, and that there are divergences in the common stars that would have been difficult to explain if Ptolemy hadn't made his own observations. Now for me, I think the reality lies somewhere in between these two positions. I think that working in Alexandria meant that Ptolemy had access to a lot of data, including that of Hipparchus. When Ptolemy decided to make his observations, he had Hipparchus' star charts with him and was, in a sense, checking to see if they were accurate, taking into account the corrections for precession. In this sense, while Ptolemy did make all the observations he claims he did, he wasn't working in a truly independent fashion. As such, there was a strong confirmation bias going on, which would have eliminated the expected greater divergence of measurements that should have been present if Ptolemy had made his own observations completely independently of Hipparchus. As someone who teaches science to undergrads, I see this sort of effect a lot. If the students know what the answer should be, it's amazing how often they get really close to the expected number, often unintentionally making what I call canceling mistakes in order to arrive at the hoped-for result. A bit like Poseidonius did when making his measurement of the size of the Earth and coming up with a number very close to that of Eratosthenes. Another issue with the Ptolemy copied everything school is that in the case of Ptolemy's planetary theories, we don't have a record of anything or anyone he might have stolen from. While it is certainly plausible that once he included another's work in his grand synthesis, that work would basically have been deemed unnecessarily and thus lost, it seems very odd that he wouldn't have given at least the slightest credit, or that we wouldn't have a record of the work in any other historian's writings. Ptolemy is good about at least mentioning that Hipparchus did this, or Apollonius showed that. If there had been an earlier mathematician, say, Mediocrities, Samothrace or some such, who had come up with a working model for the motion of Mars, you get a sense that Ptolemy would have at least mentioned him, if for no other reason to bolster his own claim, as a way of saying, look, I'm not the only one who thinks that this is the way the model might work. Whatever happened, what we know is that it's Ptolemy who puts forward the next big step in the Almagest. So let's take a look at some of the improvements he made in the planetary models that allow him to handle the minor planets. And while we do that, you might want to go out to the podcast website, thescientificodyssey.typepad.com, to take a look at some of the resources we have there to help you visualize some of what we're talking about. By the way, the best resource I found is the Planetary Motion Simulator on the Nebraska Astronomy Applet Project site. We'll include a link to it in case you'd like to go out and play around with it one evening while you're watching reruns of The Big Bang Theory. The primary thing we'll talk about is Ptolemy's planetary theory for the 5 minor planets. While he acknowledges the equivalency of the 2 earlier models for producing the motion of the sun and moon, he adopts the eccentric model with no epicycle for the sun. The reason for this, as we said in the last episode, is that it's basically a physically simpler model. Now for the moon and the minor planets, he combines the eccentric with the deferent epicycle model. To this, he adds a couple of additional pieces that will turn out to be really important down the road when we get to the Renaissance and scientific revolution. For the inferior planets, Mercury and Venus, he has to account for the fact that they are never seen at an angle greater than maximum elongation. If you will recall from our episode titled Wanderers, these 2 planets have a maximum angular distance in the sky they can be away from the sun on the ecliptic. For Venus, it's about 47 degrees, while for Mercury, it's around 28 degrees. In order to do this, Ptolemy has to keep the epicycle from ever being on its deferent at a point that would be on the opposite side of the Earth as the sun would be. So he says that there's this invisible, and that's just like the spheres, crystalline bar that runs from the edge of the lunar sphere to the point on the solar sphere where the sun is attached. The epicycles of Mercury and Venus have to be attached to this bar so that they go around their deferent at the same rotational rate that the sun does. This prevents the planet from ever being very far away from the sun in the sky. For the superior planets of Mars, Jupiter, and Saturn, he has to account for the fact that their retrograde motion always happens when they are in opposition, or exactly opposite the sun in the sky, which would be due south at midnight. To do this, he says that while the deferent can rotate at whatever speed is given by the planet's tropical period, i.e. the time it takes for the planet to go all the way through the zodiacal constellations, the epicycle for the planet must turn at a rate that is identical to the rate that the sun's deferent turns. This ensures that the planet's motion will only reverse direction at the right time of the motion. Unlike the case with the crystalline bar in the inferior planets, Ptolemy doesn't explain how this synchronization takes place. By the way, as a side note, Ptolemy is one of the first astronomers to list the planets in the order they are usually seen in when discussing the geocentric model, with the moon being the closest to the Earth, then Mercury, then Venus, followed by the Sun, with the last 3 being in order Mars, Jupiter, and Saturn. Early lists often place the sphere of the Sun just outside the sphere of the Moon. In another important work, The Planetary Hypothesis, Ptolemy also does something that no one else had done, and that is build a completely self-consistent model of the entire universe with the ratios of the sizes of each deferent and epicycle for each of the planets. He does this by using an improved version of Aristarchus's moon distance calculation based on the size of the Earth. From this, he's able to use trigonometry to scale the various triangles for the specific configurations of both the inferior and superior planets to come up with a total size of the universe that was about 10,000 times the diameter of the Earth. It should be understood that this value was shocking for the time in its enormity. While it may seem small when compared to our modern understanding of the scale of the universe, it expanded humanity's conception of the size of the cosmos by at least an order of magnitude, if not more. Now, if one were to use this model to predict the motion of the planets through the sky, one could get pretty close to making accurate predictions over the course of a few months within a couple of degrees for the planet's motions. But that's no longer good enough. By this time, Babylonian astrology has made its way into every nook and cranny of the Roman Empire. By the end of the 1st century CE, every magistrate wanted to know if the time was fortuitous to start a public works project, build a temple to the divine Augustus, or embark on some sort of military campaign. Merchants and businessmen wanted to know if a trade voyage or new partnership would be auspicious. To get a sense of how important this was, it can be noted that our words influence and influenza come to us through the Latin words that mean either a visitation of or an emanation from the stars. As Mike Duncan notes several times in his History of Rome podcast, the Romans were a deeply superstitious people, and the arcane portents of astrology hit their sweet spot for divination. However, for a practicer of astrology to be truly successful, he or she had to be able to predict the positions of all 7 planets at some future time with pretty good precision. Telling the advisors of Trajan that the positions of Jupiter and Mars were going to be in one place when he launched some military action across the Danube, and then having them in some other constellation was a good way to end up on the wrong end of a spear or as lion food in the Flavian amphitheater. To deal with this greater need for accuracy in modeling, Ptolemy introduced what was his most controversial innovation, something called the equant. What the equant was a point opposite the center of the deferent from the stationary Earth. Remember that in the eccentric model, the Earth wasn't at the center of all the deferents, but shifted off that center by some amount. The equant would be an equal distance on the other side of the center from the eccentric. Now, what Ptolemy said was that when the deferent turned, it would turn in such a way that it would look to an observer standing at the equant that a point that the planet or epicycle was attached to on the deferent would be moving at a constant speed. This meant that when the point was on the same side of the deferent as the equant, it would move more slowly, and when it was on the other side, it would move more quickly. In other words, the deferent no longer rotates at a constant velocity around its center. It doesn't turn at a constant rate. To see this, it's probably best to go take a look at the resources we put up on our website. Now, this is a totally ad hoc solution. Ptolemy has no good reason why the natural world should be this way other than to say that the device produced more accurate predictions of the motions of the planets. It should also be noted that the entire model has now broken almost all of the rules for the motions of objects in the celestial realm that Aristotle had put forth, with the exception of the motions having to be in circles. The Earth is no longer the true center of the cosmos. It is no longer the center of all circular motion, and now, with the equant, things no longer travel at constant velocity on their spheres. The only thing left is that the structure has to still be built exclusively out of spheres. Because of this rejection of the principles of celestial physics as has been put forth by Aristotle, the model, especially the equant piece, was criticized by the natural philosophers of the time and natural philosophers a millennia later. Nevertheless, as an astronomical model, it was far and away the most accurate in making predictions, and it did allow for an unmoving Earth, thus preserving the terrestrial physics of the time. Because of its comprehensive nature and its ability to create a model of planetary motion that worked, the Almagest became the de facto standard of astronomical knowledge from the time it was published for nearly the next 1600 years. In fact, after its publication, there is no other significant advancement in astronomy in the classical world that follows. While there are other astronomical treatises published, they are usually compilations of less technical works meant to serve as primers and instructional texts, as was the case with something known as the Little Astronomy, which collected the relevant astronomical and mathematical works of earlier writers such as Euclid, Theodosius of Bithynia, and Autolycus. The other type of work that you tend to see are commentaries on the Almagest itself that added little to the body of astronomical knowledge. The reasons for this stagnation are complex, but likely come down to 3 basic ideas. First, the Almagest is about the best anybody's going to be able to do. It preserves terrestrial physics while giving a good explanation of celestial motion. It's really pretty unlikely that, given the assumption of a stationary Earth, any other model would have been able to do better. Second, at the end of the 2nd century, The combination of the Antonine Plague and the resulting political instability and warfare created by the Roman 3rd century crisis likely either killed or disrupted a number of potential scholars from being able to make significant progress. Finally, as the Roman education system and social hierarchy calcified in the late 2nd century, it is unlikely that many bright young thinkers would have pursued careers in mathematics, and even fewer would have gravitated towards natural philosophy. With the rise of Christianity in the empire in the late 3rd and 4th centuries CE, many moved to work in theology, content to accept that Ptolemy's description of the heavens was more than sufficient. What I see in this is a culture-wide developing failure to question assumptions once a working explanation is found. And while it is easy to criticize this failure from the comfort of our 21st century world, the willingness to accept what works in a time of great change and instability is really completely understandable. When you're worried about how to stop Germanic tribes from crossing into your territory to pillage and plunder, esoteric questions about what causes the planets to move in the heavens become a bit trivial, if you know what I mean. It is at this point that we'll wrap up the episode for this week. As was the case in our series on the history of the atom, things will begin to deteriorate in terms of people doing new and innovative scientific work in the Roman Empire. However, unlike with atomic theory, there will be those who will not just transmit the information, but who will build on, refine, and extend it in the period of Arabic science. After another cultural supplement, we'll take a look at the work of astronomers of the Arabian Peninsula and beyond. In closing, let me take a moment to acknowledge my sources and inputs for the last several episodes. I've already mentioned James Evans' book, The History and Practice of Ancient Astronomy, as a major source of the content I've covered. Also, I've used Michael Hoskins' The History of Astronomy, A Very Short Introduction, from the excellent Oxford University Press, A Very Short Introduction series. Additionally, I would like to say thanks to my colleague Dr. Todd Timberlake at Berry College, whose class on the Copernican Revolution was very helpful in getting a much better sense of the work done by Ptolemy. Dr. Timberlake has been very generous in the giving of his time and understanding through a number of conversations related to each ancient astronomer's contributions, as well as the ideas of scientific realism and instrumentalism. His knowledge of the primary sources has been vital in creating a coherent narrative for the last several podcast episodes. Finally, I have to again acknowledge the Blue Dot Sessions for letting us feature their compositions in the show. They've allowed us to set the mood and the atmosphere for this entire series, and I know that a number of you appreciate it as much as I do. If you'd like to hear more of their work, go to www.sessions.blue. Next time, we'll travel to the mountains and jungles of South America to see the sky through new eyes. Until then, full sails on your journey.